Thank you. Oh, stand over here. Oh, I see. Okay, sure. Yeah. Thank you for the great introduction, Mary. So I'll give a quick overview of our understanding of earthquakes in Eastern Canada. So today, like I mentioned, I'll be talking about an overview on hazards in Canada, and then tomorrow I'll have a presentation where I'll kind of dive a bit deeper into kind of the fundamentals of the PSHA model in the 5th generation and the 6th generation model. When I say 5th generation model, this is the model that was included in the 2015 edition of the building code. The 6th generation is our new model, which is currently proposed for inclusion in the 2020 edition of the building code, which is set to go for public comment in early January, and then would come into force on a national level by the end of 2020. So context, damaging earthquakes happen in Canada, and there are examples of damaging earthquakes in Eastern Canada. So a couple of noteworthy ones would be, the Charlevoix event in 1925. There's the Grand Banks event in 1929, which caused a local tsunami in the region and actually led to some deaths. And other more famous examples like the Saginai earthquake. And several other pre-1900s events. You'll notice that a lot of them are in the Charlevoix region, and another one that we know about in the Montreal region. So there is certainly context for, despite Eastern Canada being in what we call a stable region, it's still a region where we do experience rare and large damaging earthquakes. So just a couple examples of these. So there's a magnitude 5.9 earthquake in Saginai, Quebec. In some regard, people say that this earthquake was a bit of a surprise, and then I'll talk a little bit more of that in a moment. And on the left-hand scale, it's kind of a depiction of what the felt intensity was from this earthquake. So you see close to the epicenter where the earthquake originated, we had intensities, on the order of 6 to 7, which is where we expect damage, especially in structures that may not be well designed. And on the right, we have an image that comes actually from Montreal. So this is several hundred kilometers away from Saguenay, where you can see there was some damage, some stuff falling off the building. A more recent example would be the 2010 magnitude 5 Val de Bois earthquake. This occurred in what we call the Western Quebec seismic zone, right over here, and just some images showing the kind of damage that was experienced. There was embankment failures, there was some landslides, a little bit of damage in, in stores. Nothing significant, but certainly is a nice reminder, especially to people in Ottawa, that earthquakes do occur in this region. This was one of the strongest shaking that we have in kind of recent history recorded in the Ottawa region. So map we like to show, so a map of recorded earthquakes in Canada. Your eyes will immediately focus, in places where there's a lot of bright red. Of course, Western Canada is a hotspot of this, but Southeastern Canada is also a region where we get earthquakes, and we'll go a little bit through detail as to why we believe this is the cause. So we can subdivide Canada into kind of different tectonic regions. So we have the more tectonically active region in the West Coast, and then we have, interface events and in-slab events. But then in Eastern and Central Canada, we have is called stable crust. We're in the interior of the North American plate, and it's tectonically has been stable for millions of years. But we can subdivide this a little bit further, and this is what we do in our hazard model, is we have what we call the stable cratonic core, and then we have the stable crust, but with clusters of seismicity. And this is important because in our hazard model, even though in central Canada we don't have many very earthquakes, there's still the capacity to have, albeit very rare events. And so one of the projects as part of the National Seismic Hazard Assessment is to try and quantify what the hazard is in these very low hazard regions. And the way we do this oftentimes is we look for global analogs. So we can look at the actual seismicity we have in the Canadian stable craton, but then we can also look on a global context to see what is the seismicity elsewhere. And we make various ergodic assumptions that if we can look at similar tectonic regions, we might be able to get a bigger data set So we might be able to do a better characterization of the seismicity in Canada. Because if we were only to use the seismicity in Canada, we don't have a large history to be able to look at, to be able to determine how often these earthquakes occur. And on the right is just a couple of magnitude recurrence curves. I'll have a couple of those in the presentation. And the way you read these is on the bottom, it's magnitude, and on the left, it's the cumulative rate. So you would read this as, per annum. So 0.1 would mean that there is roughly one of those events every 10 years. And then so you would look to see where the line crosses. So for example, if we look at the African stable craton, we would say, we have a magnitude 6 earthquake, on the ballpark of every, so that's 100 years, that's every 10 years. And then so you could go, so that's 50 years, so 30 years, something like that. And then so we combine all of these in order to help better characterize the rates. And so we combine them into what we call a world stable craton core seismicity. And then we include different versions of this in a kind of a logic tree format to try and assess what the rates are in the stable cratonic core in Canada. And these rates are relatively small, but they're still important because there's still the potential for hazard. All of these acronyms aren't terribly important, so I'm just going to skip over it. So that's the stable cratonic core. And then we have the rest of Eastern Canada, and I mentioned that we have these kind of clusters of seismicity. And typically when we're doing a seismic hazard assessment, what we try to do is we try to group regions of similar seismicity and then estimate the activity rate in them. And so you might, so it's effectively what I say on this slide. But what you want to do is you might draw kind of general regions and try to group them into like terms. For example, we have the Western Quebec seismic zone, we have the Charlevoix seismic zone, or the Northern Appalachian seismic zones. And this is a very broad grouping of seismicity that are roughly similar and correlated. And we can look at a couple of these in a little bit more detail. So if we look at the West Quebec seismic zone, historically we have had some magnitude 6s, the last one being in 1935 in Temiskaming. And before that, about a magnitude 6 in the Montreal area in 1732. And we have the more recent kind of event being in 2010. And on the map here, all these blue dots are magnitude 3s and larger. And you can see that there are some kind of distinct clusters. So when we're doing a seismic hazard analysis, we might kind of group these into kind of individual clusters. These are just roughly drawn, they're not the actual ones in the model. And then we estimate what the recurrence or how often earthquakes occur in these individual sources. And so here's example Gatineau. And so the Gatineau source of all earthquakes, and again, a recurrence diagram. And again, you would look at this and say, we expect in the Gatineau source, magnitude 5 earthquake, on the order of between every 100 years to every 50 years. A source closer to here, the Western Lake Ontario source, if I flip between these, you can see that the activity rate is dropping because the cumulative rates on the magnitude recurrence curve is dropping. Next, one of the other very important sources in Eastern Canada is Charlevoix region. And you notice at the beginning when I was talking about the history of damaging earthquakes, a lot of these were in Charlevoix, so it should be no surprise that Charlevoix is the most seismically active region in Eastern Canada, and in our recorded history, we have 5 magnitude 6s that we know about, and so certainly we expect in this region, at least in the short term, will continue to have the capacity to have these large earthquakes that could be potentially damaging. So I've mentioned that we take these kind of our viewpoint of historical seismicity, we define seismic sources and we use that to quantify future earthquakes. But is this always true? Can we use present day seismicity to say something about future seismicity? And I mentioned that the Saginai earthquake was a bit of a surprise. So prior to 1988, there were no recorded magnitude 3 events by the Geological Survey and its predecessors in the preceding 50 years. So effectively, the hazard in the Saginai region was not thought to be as high as we know it now. And so the question arises, will future large earthquakes occur in regions where we have present-day seismicity? And one of the very interesting areas of research that has been going on in Central and Eastern North America and in other intraplate settings is, what if present-day earthquakes are just really long-lived aftershock sequences of historical large earthquakes? And perhaps the future magnitude 7 earthquake might not necessarily be in that spot. It might be in a tectonically similar spot, but not necessarily where we have present-day seismicity. So this is one of the things we try to quantify in the hazard model. So again, this is just showing that this earthquake, so this red dot here is the Saginai event. And prior to 1988, there was no seismic source that effectively encompassed this. So it was what people say is the surprise. So we try to mitigate against that in the seismic hazard model by not only having seismic sources which are a reflection of the present day historical seismicity, but also based on tectonic features where we believe there might be the higher likelihood of larger damaging earthquakes. And the large tectonic feature in Eastern Canada is this rift system. Oftentimes is referred to as the St. Lawrence Valley Rift System. And effectively what it was about 400 to 600 million years ago, there was the Iapetus Ocean that opened up and then closed. So along this rifted region, kind of along the St. Lawrence corridor, it's actually the edge of a historic tectonic plate. So the crust in this region is much weaker, has more faulting, and so might have the capacity to have larger earthquakes. So in the seismic hazard model, we say that any region kind of along this rift might be equally as likely to have these future earthquakes, whether or not there are present-day earthquakes in these features or not. And other features are, for instance, the Ottawa-Bonnechere Graben. There's basically a failed arm of this rift system. And the other kind of tectonic feature in this region is the Western Quebec seismic zone. So this is the Gatineau seismic zone I showed previously. So one of the more accepted theories of why we have seismicity in that region is hundreds of millions of years ago, the North American plate was moving over what we call a hotspot, which is kind of a mantle plume. And that's, again, caused the crust in that region to be slightly more fractured, slightly more weaker, and it's reflected in a higher rate of seismic activity today. So really the image in Eastern Canada is, in regions where the crust has been previously weakened in relatively recent historic times, is more susceptible to earthquakes today. And this is just drawing those kind of boundaries in West Quebec, and perhaps, now we're not subdividing into such smaller sources, but in more regional tectonic-based features. So in the seismic hazard model, we give different weights to these models. For instance, we have the historical model, which I've mentioned is just basically trying to group the present-day historical seismicity. And then we have the regional model, which is more of a tectonically derived model. And then we also have the hybrid model, which is basically a comparison or a merge of the two. We say that the historical rates of activity are appropriate for smaller events, less than 6.8. We expect that to have magnitude 6, less than about 6.5 events, very likely in the regions we see present-day seismicity, but that these large events might actually be more governed by the tectonic features, in which case we believe the regional model. The other aspect when we're doing seismic hazard analysis is ground motion models. So we have seismic sources which we characterize the rates of earthquakes, but in order to estimate the hazard, we have to know how strong will the shaking be from a particularly sized earthquake. And we use ground motion models for that. And here's just an example of the NGA East data set, which compiled ground motions from across Central and Eastern North America. And on the right-hand scale, it's kind of give you a sense of what kind of data we have available as a function of distance. So that's between the recording site and the earthquake and magnitude. And the thing I will point out is, from a hazard analysis, it's really this box that we care about. And this is, I would say, a generously drawn box. In reality, I might even say that it's really the stuff in this top left corner that matters. And you can see that we do not have a lot of recordings. And because we don't have a lot of recordings, there's a lot of uncertainty as to what the ground motion models are in Central and Eastern North America. So we have a lack of observations. And when we have a lack of observations in a seismic hazard analysis, it means we have a lot of uncertainty. And a lot of uncertainty sometimes can drive hazard higher. So in the 5th generation model, we use the Atkinson and Adams representative sweep ground motions. In the 6th generation model, we're doing a split weighting between the Atkinson and Adams relations and the new NGA East model that's just come out recently this year, which is a big decade-long plus project to characterize ground motions and their spread and uncertainty. And I'll be touching more on these tomorrow. But after we have both of those together, we can then estimate seismic hazard. So when we make seismic hazard maps through a probabilistic seismic hazard analysis, we often can present maps in 2 different ways. One of them is in a way that depicts what is the probability at any particular location of experiencing a certain amplitude of ground motion. The other way, the more common way it's presented, is what kind of ground motions are expected at a fixed probability level. And so in the National Building Code, we develop seismic hazard estimates at the 2% chance in 50 years. So that means we want to know what is the ground motion that I can expect with a 2% chance in the next 50 years, that it will be that or larger. And this is what we do on the map on the left-hand scale for southeastern Canada. And you can see that the seismic hazard follows the kind of previous examples I showed you. We have various hotspots like the Charlevoix and the West Quebec and Montreal, but then we also can see these tectonic features that are included in the model. And on the right-hand side is a hazard deaggregation. And what this tries to do is tries to step away and say, what are all the contributing sources to my hazard in my particular location? And you can see that for a SA of 0.2, so this is a short period spectral acceleration that a small short building would be sensitive to, is largely coming from distances less than 100 kilometers and in the magnitude range of 6 and above. And this is the same thing just for another spectral acceleration. In the building code, we do this for a range of periods because different buildings react to different periods. And so we try to assess the seismic hazard for all of these different periods. So we do all of that. And then at the end of it, one of the things we like to do is to come up with a relative map to kind of depict what is the relative hazard in Eastern and all of Canada. And just to put some numbers on here, so in Charlevoix, we expect to have a magnitude 6 or larger on the order of every 50 to 100 years. The last one being, in 1925. In the West Quebec zone, we expect a magnitude 6 or larger on the order of, 150 years. The last being in 1935. And just for context, if we look at southwestern British Columbia and Vancouver Island, we expect a magnitude 6 on the order of every 50 years. The last one being the 2001 Nisqually earthquake. And again, Cascadia is where we get these magnitude 9 events on the order of every 400 or 500 years. So, in summary, seismicity in Eastern Canada is really concentrated in zones where the crust have been previously weakened, such as in previously rifted zones. And the big question in Eastern Canada and other stable crust regions is, will the next large earthquake occur in a zone of elevated historical seismicity or on an identified feature such as the Paleozoic rifts or on some yet to be discovered feature? Thank you very much.